नमस्कारम स्टूडेंट्स, आज हम यूनिट 8 थर्ड सेमेस्टर केमिस्ट्री बीएससी के मल्टीपल चॉइस क्वेश्चंस करने जा रहे हैं। फर्स्ट टॉपिक इज इलेक्ट्रॉनिक स्पेक्ट्रा ऑफ ट्रांजिशन मेटल कॉम्प्लेक्सेस। क्वेश्चन नंबर फर्स्ट, व्हाट टाइप ऑफ इलेक्ट्रॉनिक ट्रांजिशंस आर कॉमनली ऑब्जर्व्ड इन ट्रांजिशन मेटल कॉम्प्लेक्स? ए ऑप्शन पाई टू पाई स्टार ट्रांजिशन, बी ऑप्शन सिग्मा टू सिग्मा स्टार ट्रांजिशंस, C option D to D transitions, D option N to pi star transitions, and the answer is D to D transitions. So transition metal complexes often exhibit D to D transitions which involve the excitation of electrons within the d orbitals. These transitions are responsible for the characteristic colors of these complexes. Which of the following is a selection rule for DD transitions in transition metal complexes? A. Spin selection rule, B. Laporte selection rule, C. both A and B, and D is none of the above. And the answer is option number C, both A and B. The selection rules for DD transitions include the spin selection rule, which requires that the spin state must not change during the transition, and the Laporte selection rule, which states that transitions are forbidden if there is no change in parity symmetry. Next question, what is the spectroscopic ground state term symbol for a D1 electronic configuration? Option number A 3p, option number B 2d, option number C 4f, option number D 5d, and the answer is option number B 2d. For a D1 configuration, the spectroscopic ground state term symbol is 2d, which denotes a double state with a D term. Next topic is spectrochemical series. Which of the following ligands is expected to produce the largest crystal field splitting in an octahedral field? Option number A I negative, option number B H2O, option number C NS3, option number D Cn negative, and the answer is Cn negative, cyanide. According to the spectrochemical series, Cn negative is a strong field ligand and produces a large crystal field splitting compared to I negative, H2O and NS3. Next question, the spectrochemical series arrange ligands based on their ability to, option number A donate electrons to the metal center, option number B split the d orbital energies of the metal center, option number C form ionic bonds with the metal center, option number D increase the metal's oxidation state, and the answer is option number B split the d orbital energies of the metal center. Explanation, the spectrochemical series ranks ligands based on their ability to cause crystal field splitting, affecting the energy levels of the metal's d orbital. Next question, which of the following correctly represents the position of ligands in the spectrochemical series from weakest to strongest field? Option number first I negative, H2O, NS3, Cn. Then option number B Cn negative, NS3, H2O and I negative. Option number C H2O, I negative, Cn negative, NS3. Option number D NH3, Cn negative, H2O and I negative. The correct order is option number A, that is I negative, the weakest, then H2O, then NH3, and the strongest is what? Cn negative, cyanide. The correct order in the spectrochemical series from weakest to strongest field ligands is I negative, H2O, then NH3 and then Cn negative. Topic third is oral energy level diagram and electronic spectrum of TiH2O whole 6 plus 3. So what is it? In a orgel, it's orgel, right? In an orgel energy level diagram, For a D1 configuration, the ground state term symbol is 2D, 3F, 4S or FD, 5D, and the answer is option number A, that is 2D. For a D1 configuration, the ground state term symbol is 2D, which reflects a doublet state. Next question. The electronic spectrum of TiS2O whole 6 plus 3 shows a single board absorption band due to option number A, ligand to metal charge transfer, option number B, metal to ligand charge transfer, option number C, DD transition, option number D, spin forbidden transition, and the answer is option number C, DD transition. The single board absorption band in the electronic spectrum of TiS2O whole 6 plus 3 is due to a transition of DD, यानी कि DD transition, specifically from the T2G to the EG orbitals in an octahedral field. Next question. The color observed for TiS2O whole 6 plus 3 is due to emission of light, absorption of light in the UV region, absorption of light in the visible region, absorption of light in the infrared region, and the answer is option number C, absorption of light in the visible region. Explanation. The color of TiS2O whole 6 plus 3 arises from the absorption of light in the visible region due to electronic transitions with the d orbitals. Next topic, magnetic properties of transition metal complexes. First question, which type of magnetic behavior is characterized by the presence of unpaired electrons? First, diamagnetism, second, paramagnetism, third, ferromagnetism, and fourth, antiferromagnetism, and the answer is option number B, paramagnetism. So paramagnetism is characterized by the presence of unpaired electrons which align with an external magnetic field causing a net magnetic movement. Next question. The magnetic susceptibility of a transition metal complex can be determined using UV vis spectroscopy, NMR spectroscopy, covalence mass spectrometer, and the answer is covalence. The magnetic susceptibility of a transition metal complex is often measured using a covalence, which determines the magnetic moment by measuring the force exerted on a sample in a magnetic field. Next question. The spin only formula for calculating magnetic moment is, formula बताना है simply हमें, तो इसका आंसर क्या होगा? ऑप्शन नंबर A, that is mu equals to n plus 1 whole square bm. The spin only formula for calculating the magnetic moment mu in Bohr magnetons bm is mu is equals to square note n plus 1, where n is the number of unpaired electrons. Next topic is LS coupling. So LS coupling is significant in determining the magnetic properties of light atoms, heavy atoms, only diamagnetic substances, organic molecule, and the answer is heavy atoms. LS coupling, Russell-Saunders coupling, is significant for heavy atoms where the spin orbit interaction is strong, affecting their magnetic properties. Next question. In LS coupling, the total angular momentum J is given by J is equals to L plus S, J is equals to L minus S, J is equals to L plus L, L minus X, or J is equals to L into S, and the answer is option number C, J is equals to L plus S and L minus S. The total angular momentum J in LS coupling can be L plus S or L minus S depending on the relative orientations of the orbital angular momentum L and spin angular momentum S. Now, which of the following describes the interaction between the spin and orbital angular momentum in LS coupling? It only affects the energy levels of diamagnetic substances. It causes a splitting of energy levels influencing the magnetic properties. It is irrelevant for transition metal complexes. It results in the complete cancellation of magnetic moments, and the answer is option number B. It causes a splitting of energy levels influencing the magnetic properties. What is the explanation now? In LS coupling, the interaction between spin and orbital angular momentum causes a splitting of energy levels which affects the magnetic properties of the atom or ion. That's it for today's video. Please subscribe to my channel, like, share and comment. Thank you.